One of the days of EXAG.
All right, everyone, let's get started.
Just died for good.
Up next, we have generating puzzle progressions to study mental model matching.
Is there a mic or anything?
You will have to project.
Oh no. All right. Hey everybody. So I'm Chris Martin. So I'm an assistant professor at NC State University, and I'm very excited to be here at EXAG and presenting this work on generating puzzle progressions to study mental model matching, which I worked on over this past summer with my undergraduate mentees at NC State, Aaron Williams and Ryan Alexander, and was co-mentoring them with my PhD student, Shimai DePaul. So,
you may need to click through it, installing the driver.
Installing a driver. Oh dear. Okay.
Well, it isn't really installing a driver, just that whenever you plug in something the Mac thinks is a new keyboard, it wants you to tell it.
It would help
Oh.
if I plugged
Just click continue and close it.
I think the X tab. Yeah, you can just close it.
Yeah.
Okay. All right. Okay. So what we're talking about in this project, the subject of interest is puzzle game mastery. So what we're talking about is the kind of puzzle games that are featured in screenshots on the slide: Cosmic Express, The Swapper, Steven Sausage Roll, Snakebird, and Portal. So if you're familiar with any of these games, you've probably experienced the process of gradually developing mastery by playing through some very difficult sequences of puzzles. Typically, you start out with some sort of gradually, gently introduced mechanics to the puzzle, and then as you go, you eventually encounter a puzzle where you get stuck. And getting stuck causes you to get frustrated and try a bunch of different things, and eventually you have to approach the puzzle from a different direction and learn something new about how the mechanics work. So the hypothesis is that this process will tell us something about, will tell us something about how mental models work when people play games. So a mental model is something that is it's a term from cognitive science that basically is a knowledge representation, which we can think of as a simulation of an external reality that lives inside of our brains, right? And it can be used both to predict what is going to happen when we interact in a particular way, and it can be used to explain what does happen when we actually do something. So, so somehow puzzle games are doing something very interesting with our mental models, and this project is trying to figure out what. As some preliminary work for this project, my student Ryan gave a subjective difficulty evaluation to each of the levels in Portal and plotted it against this graph, and kind of confirmed some puzzle design folklore, which sort of identified, well, so puzzles in games are interesting because we can present them as progressions. It's not just a single puzzle, it's not just an escape the room where you have to figure out one little trick at a time. It's something where you're encountering the same mechanics time after time, but you're kind of learning something new as you go. So as you build in the process of building mastery, you can see that sometimes the difficulty increases as you're asked to apply what you know in a more complex setting. And sometimes, however, it kind of stays the same or even gets easier for a little bit as you continue to gain practice with what you already know. So the long-term goal for this work is to try to use what we're learning about mental models to procedurally generate puzzle sequences that support this kind of deep mastery construction. And as a roadmap for how to get there, we first think we need to do a little bit more to try to understand the cognitive science of puzzle mastery. And then once we have that, the kind of big goal out in the future is to implement a cognitive agent that can be used to evaluate procedurally generated levels. So this paper is about the first step, trying to understand the cognitive science. And what we did is we built a set of puzzle mechanics and puzzle scripts and a bunch of custom handcrafted levels. My student Aaron wrote a progression generator, and then we developed a survey to try to understand how mental models develop as players go through the game. So I will proceed by kind of explaining these first two bullets, which are the necessary background. The third bullet, which is the game that we created. Regression generation is about how we actually generated the two test conditions for our survey, and then I'll describe the survey and our future work. Okay, so mental model matching theory, given that we kind of know what a mental model is, that it's some simulation of an external reality, we can explore this theory around how games build mental models. Okay, and this consists of a few things. So I'm going to situate this in an example, which is imagine that you're, in the context of when the original Super Mario Brothers was released, you don't have a whole lot of external conventions to rely on and to bring in to inform your understanding of what's going on in a level, and you're trying to figure out what to do. There's actually a great YouTube video that I've cited at the bottom, which goes through in sort of microscopic detail how the level design of Super Mario Brothers 1-1 was used to scaffold this experience. So you have this NES gamepad, and you have some directional movement and some A and B buttons. And well, the first thing you notice is that there's a lot of empty space to your right, and so you can start building some rules. You can start building a mental model consisting of kind of a mapping from what you do and what you expect to happen. So you first notice if I press right, Mario goes right. If I press A, Mario jumps. All right. So the next thing that happens is this little mushroom shape, angry mushroom appears on the screen. And you have to kind of make a decision about what to do because you're proceeding to the right, it's proceeding to the left towards you, and you probably can predict, based on your mental model of motion and physics, that you're going to collide. However, you have no idea what's going to happen when you collide. So suppose you go ahead and let that happen, you die. Too bad, you didn't make it very far through the level, but that's okay, you can just restart. So then you can add that to your mental model. One of the things that mental models do is they generalize, right? We encounter some examples and we start to abstract and we say, maybe it's not just that specific mushroom-shaped thing. I can kind of pattern match on this object and maybe make a hypothesis that if I collide with any mushroom-shaped thing, it's going to be bad news. And then what we can do is apply our generalizations. So, all right, a new mushroom-shaped thing is heading towards me. I now predict that I'm going to die. But in fact, that's not what happens. Instead, I get bigger and, hey, that turns out to be a good thing. So what we have to do is delete this inference from our mental model and revise it. So the third key component is revision. So now we make some finer distinction between the sorts of things that are happening to us depending on whether we collide with an angry mushroom or just a regular mushroom. Okay, so in summary, mental models are things that simulate external realities. They're good for making predictions and explanations. And crucially, they sort of generalize and apply, and then they're revised upon failure. So it's really important that we encounter failures in the process of playing a game, because this is what supports the alignment or the matching of our mental model with the actual rules of the game. This is one of my favorite screenshots from Celeste, a very difficult platformer which essentially reinforces the same idea. Failing means learning, so always be proud of your death count. Okay. So next we get into, okay, so this is like sort of how we learn a relatively simple model of mechanics, but what exactly is it that makes a good puzzle? Mark Brown is a game design YouTuber who has a good series on all kinds of game design principles, where he essentially studies a bunch of examples. Yes, question?
I have a quick question about the previous thing.
Yeah.
But not this last one, but before that. Is it ubiquitous that you always go down to the most narrowly defined difference between the thing you expected and the thing that actually happened? Or are there some examples where you don't go down that far?
I don't think we have a good enough model of how people work yet to know the answer to that question, but that's exactly the kind of thing we're trying to figure out. It's like, if you do encounter this kind of failure, how will the mental model be revised, right? Do you kind of try to make as general of a rule as you can, or are you sort of, are people more conservative? Or are there situations where you distinguish those two types of revision?
Do you have examples of both, or?
Not on hand.
Okay.
No,
Okay.
I'd be,
yeah, no worries. That's true.
Yeah, thanks. All right. So Mark Brown is kind of established. So Mark Brown studied a bunch of puzzle games. I was kind of trying to figure out, well, like, what makes these tick? What distinguishes good puzzle design from great puzzle design? Well, one thing is that the mechanics have to be sufficiently clever, and what he means by that is really just that they have to have some kind of interesting emergent dynamics that can be used to build upon and slowly reveal throughout the process of solving different puzzles that depend on them. So I'll use Cosmic Express as an example here. This little video just illustrates how Cosmic Express works. So your job is to build a train track from the entrance to the exit for a train, and along the way you have to pick up every passenger and take them to a matching box. And if you do that successfully, you click play, the train runs, picks up your passengers, and drops them off. The clever mechanics in this game, or the ironclad rules and limitations that never change, in Cosmic Express are that the tracks cannot cross over one another. Each passenger has to be taken to a matching box. The train car can only, each train car only holds one passenger. In some levels you have multiple train cars. And passengers will try to hop into any empty car that passes them. This is interesting emergent mechanics that you will sort of gradually learn as you attempt various things that you naively may expect to work, like running a track directly between two of these little aliens, and then they'll actually collide and miss their train. So once you have this foundation, what makes a good puzzle from here is essentially a pattern that Mark Brown has observed that takes place as a sequence of experiences by the player, right? This is kind of like the makeup of an aha moment, is you make some assumption about the way that you're supposed to solve the puzzle. You encounter a catch, which stops you in your tracks and makes you realize that what you're doing won't work. And then you have some kind of revelation that eventually gets you to approach the puzzle in a different direction. So, using Cosmic Express as an example again, so you may make this assumption that, well, there's 4 aliens, each next to one little matching box. Surely I should just be able to get my aliens over to the box nearest to it. And then you quickly encounter the catch, which is that, well, it has to do with the fact that tracks can't cross over each other, right? So you kind of keep running into yourself if you just try the naive approach of winding this track next to try to get the aliens next to the box that they encounter. And if you still have one with you when you reach the exit, you don't successfully complete the level. Okay, and the revelation here is that, well, it has to do with the fact that there's some kind of conspicuous empty space, both above and below the sort of center of the puzzle here. And you would start to kind of understand that you can use that in order to double back on yourself in a particular way to solve this puzzle. And in fact, it breaks your assumption by taking, if you watch the top left passenger goes down to the bottom left box, and that one swaps with it. So that's the solution to that puzzle. So our research question is about the relationship between kind of this theory and mental model alignment theory, where the latter is something that's been very sort of rigorously scientifically validated, and assumption catch revelation is something that some YouTuber made up, right? That seems like a pretty good explanation, but can we actually try to test it and figure out if there's some relationship here? Okay, so the last game I'm going to explain to you, in detail at least. So this is our game called Laserverse, which we made in PuzzleScript, which is a great tool for prototyping puzzle games. And it's a pretty straightforward iteration of a mechanic I'm sure many of you have seen before, which is lasers and mirrors. And the little yellow spinny things indicate that you can rotate the object. So your character can move around and start rotating mirrors. Lasers obviously bounce off of mirrors at 90-degree angles, and when they hit sensors, they activate wires that connect to things, such as additional lasers, and that eventually allows you to get through the exit. Now this mechanic does sort of satisfy the criteria of having a lot of interesting emergent mechanics. So this is one that my student calls feedback, which is the idea that a laser can eventually become self-powering. So this is a plate where if you step on it, then step back off, it turns off, but the laser will actually stay on because it's activating a sensor that connects to it with another wire. So this is a way of getting the laser to stay on after it's been activated. Another example is a mechanic that Aaron calls beam lock, and this is another way of kind of getting the laser to stay on, or sort of splitting the beam in a particularly clever way. So to solve this puzzle, you might sort of start making this assumption that you can move the things with the pink spinning things are movable, and So you have a splitter and a mirror, and you can start moving them around, but if you do it that way, you'll quickly run into the situation where you feel like you can't get that beam to point towards the sensor, which you need it to. So the way to solve this is not to use the mirror, but to use the splitter to do this initial positioning, and then when you use the mirror over to the left, you can move the splitter to split the beam into the sensor. Okay? So there's a bunch of different emergent phenomena like this that we organized into a conceptual dependency graph, which you can kind of think of as like a prerequisite for the curriculum. Right? So there's like all these sort of different things that you can learn as you play the puzzle, and they depend on each other in different ways. Feedback depends on your understanding of lasers, sensors, and wires. Tripwire combines that with knowledge of how crates work, and Beamlog combines these two ideas of feedback and splitter merge. So then we created a progression generation to try to take advantage of these conceptual dependencies to generate level progressions that make some kind of sense. Okay, so this is a visual depiction of the data structure that we constructed. You don't need to understand the details of what all these different numbers mean. They're basically just different metrics that we use to prioritize both the selection and the ordering for the levels that we chose to include. But essentially, this structure creates a directed acyclic graph of the dependencies between the levels, which are represented as the red nodes, and the so-called learning objectives, or the concepts, which are the blue nodes. So for example, the spin tile, the blue node, is a concept that can be satisfied by any of, so sort of disjunctive, right, by any of the levels, clear as mud, FW1, or MS. Whereas crate expectations is a level that depends on the two learning objectives, buttons and roof tiles. And so this is essentially just a representation that we could use for generating the progression that represents that conceptual dependency ordering. And then for our two conditions, we use two ordering heuristics, essentially corresponding with depth first and breadth first, for how to present, for how to order the levels that don't have any dependencies between them. So the front load progression would be one where you get kind of the easy versions of the blue and pink, and then you get the slightly harder versions of them. Back load teaches you everything you need to know about the blue progression, and then tries to move on and teach you everything you need to know about the pink progression. I want to shout out to reviewer 3 who recommended this book, Make It Stick, Plans of Successful Learning, which I've now read and really have gained a lot, benefited a lot from that. So this actually teaches us something relevant to this project. So it's all about how to learn, right? How to remember and develop skills better. And this includes some best practices like spaced repetition. So you want to force yourself to recall, right? To retrieve memories rather than just rereading things. But the timing at which you do it is important. You want to basically almost forget what you know, and then ask yourself to do a recall. And that's the optimal time in order to strengthen that memory. Make it so that you can use a longer gap next time because your forgetting will slow down. So this is represented nicely in this graph by Nikki Case, who conveniently has an explorable explanation about spaced repetition. Another one of the concepts in this book is about interleaving concepts, and it refers to the sort of myth that the best way to practice something is through mass practice, through basically pushing all of your practice of one concept together until you've really got it, and then moving on and doing that for the next thing. It suggests that instead interleaving your different skills, even if you don't feel like you've gained mastery over all of them, is actually more successful. So based on this, we have some revised hypotheses from what was in our paper, which include, that perhaps this front-load approach of interleaving the concepts in our puzzles will actually support more mental models. We also hypothesized that we were collecting information about the experience that participants had with puzzles. So we have a hypothesis that both of these progressions should create the circumstance where beginners may start out more slowly, but will eventually catch up to those with more experience. And then another thing that one of our reviewers pushed us to try to consider is to evaluate whether the levels actually teach what we think that they teach, right? We've got these sort of learning objectives, and we say this level teaches this concept. but does it actually? And I think we'll be able to extract that information from the way we've designed the survey. So now on to the survey design. So when we first started trying to figure out how to test this game, we did some play testing with the lab, which I think was actually really helpful. But we veered away from our initial idea of doing a think aloud study where we would put people in front of the game and ask them to think while they were solving it. Because you run into this very interesting problem where if you ask somebody to try to make a guess about what's going to happen when they try a certain thing, and you ask them to make that guess before they do it, the buttons are right there under their hands, and they're just going to start doing it. It's like almost impossible to get people unglued from the keyboard, to actually reflect and sort of pause and like make this prediction before they move. So we kind of had this problem where people wanted that immediate feedback, wanted that opportunity to explore the mechanics before they wanted to tell us anything about their mental models. This is also reflected in Make It Stick, wherein they actually they talk a little bit about how this really immediate feedback that games often give us is not actually that good for long-term learning. You want to have to struggle a little bit, to be forced to think about what's going to happen. So what we did in order to create that circumstance is we designed a form, a Google Form survey, where we just, for every level in an 11-level sequence, we asked people to make some predictions, play the level, and explain what happens. So obviously this takes quite a long time. Some people, we gave people the option to skip the levels. Several people took advantage of that, but we did get a lot of information from this, which we're currently still processing. So in the prediction stage, we asked people to describe what they see in the level, how they think they will solve it, and what they're going to try first. And then in the explanations, we're trying to extract some differences, right, from what they actually did and what they thought was going to happen. So we asked them to tell us about what they learned about any of the mechanics, how they solved the level, why they believed it worked, and if they made any attempts to solve it that did not work, right? One of the disadvantages of doing this in a survey is we can't observe failure. So we're kind of trusting people to tell us about their failures, which may or may not wind up actually working, but we do at least have a question that tries to get people to tell us what they tried that didn't work. So we wound up with pretty good turnout for the survey. We had 50 to 60 participants for each condition. We did allow people to skip some of the levels, and some people did take advantage of that, but we still had a fairly substantial number of complete breakthroughs. And we're currently in the process of hand scoring the before and after mental models based on the textual descriptions that people gave us. So in summary of our contribution, so we developed this open source modular puzzle game that people can tinker with and perhaps use for their own research. We've developed a novel progression generation algorithm, and we had some hypotheses and an experiment design for trying to understand how puzzles facilitate mental model construction. The kind of takeaway from what we've done so far, or at least the hunch that I have that I would like to try to impress upon the PCG community, is that something like puzzle game mastery is really complex, right? It's more than just sort of something you can observe at that you can facilitate by looking at the syntax of the puzzle in a sort of shallow way. So I think this will actually require understanding of sort of the cognitive science and the mental models that people are making when they solve it. In future work, as I mentioned, we want to do procedural level generation, not just for the progressions. And then something that's a little bit, I think, a divergence from this work that I still think is quite related and interesting is the concept of problem-solving games, which you could perhaps consider a particular class of puzzle games. So these are things like Infinifactory and Factorio, where you're given kind of abstract problem specifications, like you have to create this many widgets of a certain type, and you have a bunch of building materials with which to construct machines that can do that particular activity some repeated number of times. So Mark Bradigan has a great video about this, where he distinguishes this type of puzzle from the previous types of puzzles in these terms, right? In typical puzzle games, what you're doing is discovering the solution. You're kind of trying to mind read the designer of the puzzle and try to figure out what they're communicating through these very deliberate things that they're placing throughout the level. Whereas in something that's more like a problem-solving game, you're inventing a solution. So there may be many solutions, and the designer surely hasn't actually anticipated all of them. So it's a little bit more of a kind of creative problem-solving task, perhaps. And one of the reasons I'm interested in this is because it clearly has some relationship to things like programming and engineering. And something that hasn't really been studied that thoroughly is whether games actually have, as I think many of us believe, some kind of ability to transfer skills from types of puzzle solving we're doing in games to things like programming and other types of engineering. This is Redstone in Minecraft, and someone made Pong in the game TIS 100 with electronics. So these are just games that kind of try to actually embed, directly embed programming concepts in them as mechanics. So that's all for me, but faster than I thought it would. So you can go ahead and play. This is not a particularly organized progression of the levels. This is just our whole slew of levels in a kind of cacophonous order. You are welcome to go tinker with them. There's a hack button you can press to look at the source code and mess around, maybe try to design some of your own levels. And I would be very happy to take questions at this point.
Hey, so I have a question about the overall, let's say that putting like, let's talk about first try killers. There are some stages out there, especially for the homebrew community, that for the first try, you just can't clear it. And it looks like, if you are trying to make this kind of progression in puzzle games, then you are essentially creating first try killers. You are not, you are generally trying to put something in the stage that let the player learn something by the cost of letting them fail. Do you feel that it's a way that reduce the overall, it will make player rage quit?
Oh, so you're saying this could be a way to reduce the player wanting to rage quit? Is that?
Do you feel that this goes against the assumption that games should be interesting and will cause players to rage quit?
I don't know who's making that assumption. I don't necessarily agree with that assumption. I think there are lots of games who are, games make different choices about this, right? Sometimes they assume you're coming in with, having seen a lot of games like it before, and so they're just going to try to throw their hardest stuff at you right off the bat without getting you up to speed. But I think most games do take the approach that, at least in the beginning, you need to be walked through some of the initially sort of supportive examples that help you understand what the rules even are before you can start to apply them in more complex situations. The Witness is one of these games that people are constantly talking about being one of the hardest puzzle games out there, most frustrating, right? But even that starts out with saying, like, here are two dots. You can draw a line between them. It just walks you through in baby steps how the mechanics of it actually work. So I don't think it's antithetical to that idea. Yeah.
Thanks. I found it very interesting. What you talked about in the beginning is assumption, catch, and revelation.
Yeah.
That reminded me of a concept called cognitive dissonance.
Uh-huh.
Have you come across that?
Yeah, not in the context of games, but yeah.
Okay. So.
Yeah, no, I think that's a very related idea. Yeah.
Yep.
Yes.
So this all sort of worked out because you had a set of design primitives that had depth. And I was just curious how did that work out? Because you had to know that they had depth, and then you relied on that to create more depth. So was that something that came from the experience of you and your students, or did that, you know what I'm asking?
Yeah, I think I see what you're asking. So it's kind of like, how does the step 0 have clever mechanics part work, right? That's kind of, like step 2, draw the rest of the owl kind of thing, right? So it's not necessarily clear how you develop that. I think it takes experimentation, luck, and playtesting, which is a lot of what we had. My student Aaron was the one who I think he and Ryan both collaborated on coming up with a set of mechanics, and I think they just had some good instincts and iterated on it a little bit with playtesting. So, yeah, Aaron.
Really cool talk. Thank you. I was thinking when you were talking about at the sort of foundational level of the game has these inviolable core concepts that it wants to teach you at the beginning, and then the mechanics and stuff, how a lot of puzzle games then will move on sort of once you've mastered the mechanics to sort of a second stage where they start challenging those assumptions in different ways, and sometimes in ways that require the player to forget things that they have been taught were inviolable.
Right.
So I'm curious if you and your team have thought about that at all, as you move forward into the generation stage, is whether that's a separate step or part of the same overall structure of your first teaching and then challenging those assumptions?
Yeah, that's definitely something we're thinking about. I would say that I think that at least at the lowest level, the mechanics themselves shouldn't change, because I think that tends to create the sort of situation where a puzzle solver will feel like it's unfair, right? Like they were using what they knew about. It's like, have you played Steven's Sausage Roll or something like this?
So I love puzzle games. That one I could not.
Okay, yeah, no, I didn't finish it. I got a little ways through it, but it's one of these things where it's like there was someone who wrote a blog post about it, which are like. The physics of sausages are immutable, right? It's like nothing changes about the way that the world works. It's just that you're exposed to different interesting consequences of that by being put in situations in a very strategic way that reveal them slowly.
Yeah, I mean, in a sense, that's maybe just like a twist on revising your model, right? So I was thinking of like in Portal, where early on, and this might be the second one, I forget, where you're taught like there are only certain kinds of surfaces that you can portal,
right.
And then later you learn that, oh, actually there's another kind of surface you can portal too, that is now being presented to you, right? So
yeah, that's a good
psychologically, maybe it just feels like the game's breaking the rules, but it could be just a continuation of the same refining more and more.
Right. It's sort of adding something new that causes you to pattern match incorrectly from what you have seen before. Yeah, that's a really good point.
Related, and you mentioned talking about do the levels teach the concepts that we want them to teach, and ways in which we can figure that out. I mean, how are you going to be like, well, does the player know? Like, they finished this level that ostensibly introduced this new mechanic or this new concept, and is the act of finishing the level sufficient to do that? So, like,
yeah, so I would say that so we have a question that asks people to explain what they learned when they did the level, and in some cases, like, well, maybe they just thought it was obvious that, I don't know, crates block lasers, and so they didn't bother to mention it. And I'm sure there's going to be some of that we'll have to kind of intuit from their text, but we're hoping that people will at least try to write, hey, I didn't know that the crates worked this way originally. Now I know that. Now I see that they're working in a different way, and we can hopefully map that onto the concepts we're trying to teach. Does that make sense?
Yes. The follow-up then is, even once you have that information, how are you supposed to, if you're doing this generatively, like, how are you going to represent that so that it can actually be used? Or are you just going to be like, we're going to hard code this because we hard coded everything else because we made the puzzle game, and that's just the way life goes. Like, that's fine.
Well, I mean, I think if we extract if we can get like I expect to be able to get sort of a stable set of like learning objectives that that we can use as at least a relatively small set. I'm just going to set up on questions. Okay, no worries. Yeah, thanks. Yes.
I really like the thought that went behind the design, and I completely empathize with this notion of this think a lot protocols.
Yeah.
When you have a way of doing it, and users sort of tend to just do the action instead of thinking.
Right.
I wonder if it may be able to design an experience where it's sort of like turn-taking based, where the game sort of pauses and sort of forces them to sort of predict.
Yeah.
And all the keyboards are like active, even if the instinct is to press.
That's a great, I love the idea of building something like this into a game system, especially if it's something that's designed to be educational, right?
Yes.
Like freezing the game and getting people to be more reflective. That's a really good idea. So I am out of time, but I'd love to take more questions from people in the hall. So.
Can I just grab a timer?
Okay, just FYI, that is my adapter, so you definitely use it and then return it to me after this.
I'll have you down if I don't.
All right.
Hey, I'm Kate Compton. I'm here presenting a very brief paper that I wrote called Freedom of Movement, Generative Responses to Motion Control. I'm at the Expressive Intelligence Studio refusing to graduate. So this work is definitely putting the experimental, and possibly not the word games, in experimental AI in games. My work is largely influenced by Phil Avery's critical technical practice, although a much less disciplined version of it than he did, where I make lots of small prototypes to understand and explore spaces. And then I like to experiment with new venues and new use cases. So a lot of my stuff is embedded in some sort of social context. I am the grandmother of 10,000 Twitter bots, for example, all of which are kind of operating socially. But so some of my stuff goes on web pages. Some of it is in Burning Man art festival installations. I've made furniture that is interactive in interesting ways, although not installed yet. So I'm really interested in the way that people interact with AIs and where we interact with them. So where does AI fit in our lives? My question in my paper was kind of about how does AI listen to us? And then how does AI speak to us? And where is the AI? And how it's not always a human-shaped agent. Often when we think of AI, we think of like a person or whatever a person would be in this game, that's where the AI is going. But also you can have AI that's rooms or environments, or even AI that's clothing. But today I'm going to talk about sort of AI in motion control to answer these questions in a way that I care about. And I'm explicitly interested in, does everybody know the term centaurs in AI? It's AI combined with a human, so it's not, I explicitly often reject the concept of the sort of, you have a big button that says generate and you hit the button and then dance is generated, and that's it. What else did you want? I'm very interested in how AI and humans can like play together. So why do motion control and generativity go together? I'm really into all things generative. I used to work on a game called Spore that did lots of generative things, but then even before that I did lots of weird generative experiments. One of the things that frustrates me about doing motion control, and I've been doing motion control stuff with webcams since 2005, and then recently with the Kinect and with motion, and failing to use some of the modern VR or like machine learning stuff, which I'll show you later. But this is currently our model. You have to have a computer that can listen and respond to the user. And the trouble is that our responses are often things like, we have if statements, like if you did the thing, then we'll do some like additional computer logic. And this makes it such that we actually have to compress what it can listen to into a sequence of events. And so we see this with dance a lot. Like we've all played various rhythm games probably. And these interpret dance as a sequence of button presses. And if you interpret dance as a sequence of button presses, you get something that looks kind of like that. And you know, we've seen like lots of games that are all like really engaging, fun games. Really, no shout-outs for Parappa. And even like embedded within other games, there's this kind of cliche of this like press buttons on the rhythm and now you're doing a dance. So what else can we design? So last year at EXAG, I presented this deck of cards, and I have a deck with me, and I have a couple of other decks for people to acquire if they'd like, which are all about kind of designing these generative pipelines with this idea of what are you listening to and what can you actually respond to. And so a lot of our input devices look kind of like this. These are Generative cards. So like, I have a button, and that button can generate either events or states. I can hold down the button, or I can like hit the button. And all of these kind of work in the same way. They all generate events and states, which is great, because if you want to play a sort of like Tetris or Mario or Dance Dance Revolution style video game, those eat events and states. Like there are a couple of most traditional rhythm games are just eating events and states. If you have more complicated stuff that can also, like if you've got like a thumbstick where you can also have a vector position, or even an Oculus Rift controller where you can like move your hands through these 3D spaces, they're often still just listening to the button presses. That's fine. Like you can just like take a couple of the outputs and ignore the rest, and you can play a video game. So that's great. So we had a Kinect class at UC Santa Cruz that was sponsored by Microsoft a while back. And playing a video game with a Kinect, did anybody try to design for the Kinect back in the day? A couple of people. Anybody design for Like Motion? NeuroSky? Anybody? These are actually very difficult to design for because look, none of these give you events and states. And so I have a lecture that I gave to the students that is the Kinect is not an expletive button, because I get so frustrated because what people do is they take this Kinect, this wonderful big pipeline of vector data that's like you've got maybe like 100 points of data from like 20 different vector positions moving through space, 30 frames per second, just a massive pipeline of information. And they compress that into detect gestures, button press, hold button. So it's very frustrating to just see this really interesting pipeline get turned into this because that's what we can listen to. So my question is, what are other ways we can listen to stuff? Here's something I'll be showing you a little bit later. This is a game that I made called Idle Hands, where you have the Like Motion that gives you a whole bunch of vector data. You run a Voronoi diagram on that, which eats vector data and spits out like these kind of interesting geometric shapes. And then you just render that directly into a screen. It took me an afternoon to build that, and I've been showing it at art festivals for the last 2 years. And it's very direct and very interesting, and at no point compresses that data. You can do all sorts of other weird stuff. So like a lot of art projects use the concept of shadows. This was especially popular in the early webcam days, where shadows were all you had. I can like do very simple image processing on black and white pixels and do something with that. And so to read this diagram for you, so I'm going to have some shadows, so they're going to give me a black and white depth map. I'm also going to have a webcam that gets social media from some location, or maybe like social media from some keyword. And so I'm going to get like pictures from the internet, and then I'm going to like blend those with my shadows. Like my shadow is going to be doing like cutouts of pictures, and then I'm going to project that somewhere on architecture. You can do things like voice blocking. So like a Connect has got like my body data. So imagine I had my body data, and then I have voids, little particles swarming around me. But there's no reason that I have to stop with those voids. I can use those to generate meshes with metaballs. So now I have like a sort of animated wristlet of goo orbiting my hands. So you can get really interesting stuff with this. Then I can put that in stereographic VR, why think not? So you can create these pipelines of motion control. Again, you can see my last two papers at the previous EXAG. But I'm also interested in what kind of experiences we can create with these pipelines. There's a sort of bad case. And I sometimes have to call people out if I see this, but I often just like see it in a lot of things, where the polite way of referring to this would be the game of telephone pipeline. So for example, here we have a Connect, and I'm going to detect gestures, and it's going to label those gestures as like what I am gesturing. Maybe happy or sad, or if this was face detection, it can detect happy or sad face. Like happy, sad, disgusted. This is what we'll get from our face detection. And then I'm going to search for that on Twitter. And I'm going to do a sentiment analysis of the tweets that I find. And then I'm going to use that sentiment analysis, good or bad, to like direct flocks of birds up or down, and then draw those to a screen. Am I going to get anything useful out of the end of this? The sort of impolite way of saying this, I apologize in advance, is the human centipede pipeline, where I hate to say that, but it's very vivid, and it also describes what's happening very well, which is at the end of the first one, all you're getting is random noise, and digesting random noise further is not going to get you anything out of noise. So often these ML things can like create noise in your pipeline, and then there's no directness here. It's just you're interacting with noise that's not listening anymore. So some related work that's in this space, Lumen AI is kind of the big one. This is a project out of Georgia Tech, where people are interacting with a sort of sentient, well, semi-sentient AI that has like 4 different approaches that can use of mimicking, transforming, recalling previous dances, or applying patterns. So this is like very interesting, and it got really good responses. The generativity in this case, you can see that there's like little void swarms or little particle swarms following the body. So that's kind of giving some generativity. But it's not doing a lot of surprising generativity in the positions itself. One trouble I found with these sort of improvisational approaches is often I'm not sure as a player if the AI has heard my movements right. You can get around this in a sort of way that I'm not super keen on, of telling your user that you're AI and AI is smart, and so if they think it's going wrong, then they're wrong because AI is smart. This is a common approach, and it works really well, and I'm not keen on it. But this is one of those cases where often it's, did my AI lose tracking, or is it improvising? And if I can't tell as a user or as the designer of this, something is going a little haywire, like I'm losing directness. Also, in very important related work, Mueller and Asbister's movement-based game guidelines in 2015. This is a just like giant categorical work of different ways to think about how to design movement-based games in a way that makes the movement pleasurable. And then I'd like to sort of add a caveat to my talk, which I just added today, which is that I think we need to know our domains. I'm not saying in this work that I am generating all dance, because different kinds of dance have very different sort of domains and different needs. There was one very not good AI dance paper that I read once that started off their introduction by saying dance is a sequence of positions in time, which is not my understanding of dance at all. There was actually another very good one where it was a woman who is extremely practiced in a specific kind of traditional Indian dance, which is about positions in time, using her knowledge of that dance to generate dance of that form. So I'm not saying I'm generating all dance. The things at the bottom are dance notations from different eras, all of which compress dance into the things that they care about in dance, which is wildly different, depending on whether you're like a 14th century court dance or like early 20th century modernist dance. So I'm interested in casual users with a bystander performance component that are clear, understandable, direct, and present. I like acceleration over position, so I'm not very, I don't actually care where the dancer is in space. I care whether they're making a sharp movement or a smooth one. It's not about, when your tap shoe hits the ground, it's not about you intersecting with a plane at 0. That's about the sudden stop in acceleration and force feedback on your foot. So I've gotten really good results using acceleration and forces. So I'd like to talk to you today about and my paper is kind of about these 3 buckets of ways that you can use AI in dance. And again, dance as I've described previously. One of my favorite ones is costumes, just because there's so much wonderful history in dance and across cultures of people using costumes to accentuate dance. You wouldn't think of any of these things on screen as AI, but they're all things that are operating in rules to kind of yes and motion. So we use this a lot in sport. If you like to think of sport as like having lots of AI stuff, which it did. We had a whole system called wiggles and jiggles. It was explicitly for something called secondary motion. And secondary motion is if I'm moving and my name tag and my jacket is also moving. This is really great because you can use very small motions and the secondary motion accentuates it. And suddenly that motion is exciting. This is like pure generative power. It's very emergent. It's also nice because it's got a direct causal link. It's linked directionally, temporally, locationally to what's happening. If I have bells on my hand and I move my hand, how those bells are moving is based very specifically on what's going on with my hand. There's no I'm not sure if those bells are updating or not. It's remarkably clear. It's wonderfully easy to debug. And yeah, there's a lot of really interesting exploration. So the one at the top is Nick Cave's sound suits. These are physical suits that are worn for dancers. And the one at the bottom is a project that was heavily inspired by that, where these are all generative digital suits that are being worn by people. This is pre-rendered. And then the Muppets are also a really strong example of this. A naked Muppet is actually not particularly interesting to watch. A lot of the characteristics of the Muppets, if you're ever in the Atlanta area, go to the Center for Puppetry Arts and see all the different things that Muppets are made out of. The character is in the secondary motion. So this is a project that I made at Google. This is actually why I ended up writing this paper, because I was trying to think of what I had to actually send to EXAG this year, like many of us. So this is a project that Google Creative Labs got me to make. They had this thing called PostNet coming out, which was essentially the Kinect but without a Kinect, just with a regular webcam, and I'll show you some of that later. And it was well, how do you get people in front of a webcam to actually start moving? And I read up on mask theory, I read up on sort of puppetry theory, and once you put people in a mask, this is basically giving people randomly generated costumes. And it's really easy to see once you have these costumes, once you have, has anybody put on a cape and immediately you start doing cape motions? Yeah, improv theater does this really well, is if you give people accessories, it tells them how to move. If you put somebody on stage and say move, most people freeze up. But a mask, a costume, these are really strong movement generators. So the takeaways from this section, costumes listen to gesture. They respond by accenting and exaggerating motion. They can be all sorts of different things. Here we go. Physical, extra-diegetic. I was just at the taiko drumming 50th anniversary in San Francisco, and it's a lot of dancing, but also each time you dance, you hit a giant drum. So this is accentuating your movement with a big sound. The one at the top is a Fred Astaire routine where he's actually throwing down fireworks as he's dancing. So this is explosions as a dance costume. Another one is fields. This is kind of you have a big abstract space that has some rules. And you can have all sorts of interesting, fascinating rules. It's one of the classic examples of interactive art is texturing. This was one of the early ones that got really popular. And there's just like falling stuff, and you are making sort of outlines to change how the falling text falls. But there's a lot of dance performances that are using nets now as well. TeamLab, has anybody been to a TeamLab show? They have a lot of spaces where you can kind of move around this space, and then something attractively generative happens. It's often like it doesn't even matter what's happening as long as it's responding to you. Like they're responding to your movement through the space is very exciting. So the takeaways on this one, so this is the Idle Hands project that I was showing you earlier. There's a little kid. Little kids love this. Little kids and stoners. And this is like, it's, there's like, you're listening to some sort of spatial movement, usually in a plane. The responses are often things like forces. This is all about kind of force fields. You're making like a field of some rule. Things that work well are like gravity, magnetic fields. Often my forces that I use are a weird combination of gravity and magnetism that feels good. It's like Mario physics. You just tune it until it feels right, and like Newton can go to hell. Sorry, Newton. And yeah, you're kind of creating force fields around the body. Voids, actually, particles and voids work really well in this sort of situation. Oh yeah. Okay, change the text thing. So the one on the top right is actually something that I made in response to the one on the bottom right. The one on the bottom right is using the Kinect. So it's an art project where it uses the Kinect to detect as you're like moving your hands through this sort of abstract musical instrument. But it's very static, like there's movement within the space, but there's no sort of like pushback from the screen itself. So I made something called the squishy touch screen, which is in the top right. There you go. And that's really just it. So it's a touch screen that you can mash your whole face into. It's very soft spandex stretched over on an IKEA frame with a laser projector and a Kinect. And all it's doing is it's taking the depth field and it's remapping it to color. And I've had people just like speaking to me while like recreationally stroking this thing. It's really interesting because it deals very well with a wide range of motion. So like you can touch it slowly, touch it fast, it kind of pushes back on your hand. You can mash your face into it and it actually like takes into it, like without any smarts, responds to the entire like structure of your face, which is really exciting to kind of play with. So this wouldn't be complete without talking about agents. You know, when you talk about dance partners, often people are talking about like, you know, there's an AI dance partner, it must be like a physical dance partner. Like if you've ever seen, I should have put this image in there, but the Japanese robots that provide like dance partners for like ballroom dancers. And so I do a lot of ballroom dance, or at least I used to. And one of the interesting things about when you have a partner is often you're very physically connected. So you can feel their hand on your back, pushing you back and forth. This is actually how you steer around a crowded ballroom. It's like there's just gentle pressure that tells you that somebody's behind you. Like it's very evocative and very physical and very direct when you have that connection. But these are things where like they're listening to a variety of different things, gesture, outline, image, but they respond with immediate and directly linked feedback. There's kind of a spectrum here. If you have totally connected dance partner, you actually have something that feels like a mirror. And so there's this guy called Daniel Rosen, and he does just like dozens of these different like generative mirror things with like different objects fading in or out of view. And then there's things like Chris Milk's Treachery of Sanctuary, which is a Kinect piece where your hands become like giant wings. So these both feel very much like mirrors. I'm having trouble finding examples where bodies are connected and there feels like there's agency, but feels like there's still that sort of tangible, immediate, direct connection that I feel with the real dance partner. So there's a space in there that's not being explored. Expressive connected agents, these are things like Lumen AI, but also there's kind of these other weird things where it's like, it's listening to some sort of abstraction. This is something that's like listening to the way I dance, doing some sort of squishy calculation, and then responding in a different way that's not direct. It tends to be temporally delinked. It has agency in response. This runs into that question of like, is it actually working? And often there's like, you know, how much do I trust this AI to actually identify what I'm doing? These are often described as creepy. So creepy AI scans a driver's face and voice to monitor mood and distraction levels. Like, am I okay with it like labeling my emotions? This is an example of some paper that I found where it's trying to read your emotion and then give you a song based on that. But how do you tell if that's working? Are you making the wrong frown? Is your frown not frowny enough? Does it just not have enough frown songs? These tend to be you have to lard these up with like a lot of different feedback mechanisms just to tell people what the heck is going on and what's going wrong. So yeah, where is the AI? There's just so many different places that you can put AI. I've actually found kind of an interesting thing where like living paintbrushes also fit into this space. So I have all these pictures are from a project where I was trying to do different leap motion hand tracking stuff and use it for finger painting, but then I also started using it to direct void, but then the void started painting. And so like, is this a dance partner? It feels like a dance partner in certain ways, but it also feels like a paintbrush. So kind of like Jackson Pollock style painting as a paintbrush. So I wanted to quickly show you some stuff just since we're doing interesting results. There we go. Okay, so this is the, oh, don't you dare. Oh, for the fuck of God. Sorry. Sorry, stream.
Shout out to the EXAG swear jar.
Yep. I'll put a quarter in, buy you a new microphone. All right. So this is the, I'll turn it down a little bit. This is the puppet generator. So this is basically, at this point in the project, Google had not actually released PoseNet, and so I was just like generating my own sample data based on a little like 3.js model that you can see there. I can turn off the mock body so you can just see this. Let me turn that speed down a little bit. Maybe do a different song. And then I can like re-roll different bodies. And so all of these bodies have things that are like all about secondary motion. This is basically a spore, but with just the secondary motion parts. So this is pretty fun. You can kind of imagine like if you were standing in front of this mirror and like dancing with this stuff, it would be like interestingly engaging. It's a little too tweaky right now, but you can see like each motion that it makes is just like accentuated and yes-anded by these generative things. So there's that. It was fun. But one of the interesting things, so then Google released the PoseNet stuff, which you should definitely try out. It's really interesting. And I was dismayed to find out that it didn't have Z position. It only had XY position, and I actually needed Z position to like move this three-dimensional puppet body. So then I embarked on this giant yak shaving expedition to try to figure out like, could I have a like generative body and then procedurally jiggle it until it matched these like randomly generated points. And it worked really well with this. This is just like a sort of generative limb doing that. But let's see. But this is what it's currently doing. So this is the current output of PoseNet, and I think like Frank Sinatra dancing in front of a white screen is about as good of a data as you're ever going to get. And you can see it's still having quite a bit of trouble tracking him. And then this is kind of that like multi-stage telephone pipeline. Not only is it having trouble tracking him, but like my procedural pose jiggler, like it should look like that, but it's not. So sadly, this is all kind of not working out super well. If anybody else has approaches to solve that or things that are going to do 3D depth, I'd be delighted to hear them.
Use Dense Pose for that.
Dance pose?
Dense.
Dense pose? Okay.
Yeah, competing lab, Facebook, but they do 3D stuff and it works better.
Anyway, here's my idle hands thing if anybody wants to do this. It really, you'll feel the directness when you do it. I've had numerous people tell me that it feels sticky. Oh, and here's some voice blocking, just because.
What's the input modality for that?
Leap motion.
Wow.
It's just directly leap motion, spits out a bunch of vectors. I feed that into, well, like that, doing the nice 3D pans is something else, but I feed that directly into Voronoi. I shade the Voronoi in attractive ways, and then I put some swarms on it. And I was done. All right, yeah, any questions? Yeah.
Since you're talking about using, let's say, using all the sensory data in, let's say, making games, do you feel that it's a way that will completely substitute the game we have now that deal with events, or you feel that that's a way that complements it?
Like there's every kind of game for every kind of moment. We're currently not making games that feel good to just like move around in front of. Like, does anybody still play their Wii? A couple of people, yay! Remember how like motion control was going to be the future for about 6 months there? But it didn't like click yet, and so I'm hoping that like there will be more of these moments that click. There's actually a couple of good VR experiences where you're just there's one where you on the Oculus where you're just waving these like sort of pudgy little fish particles around, and it feels like wonderful to like just wave your wizard hands and have your fish particles like oscillate around them. And it's kind of hard to design games that work with this, but I think it's not impossible. I think it's just hard. I personally have no affiliation to the game not game divide. If you care about that, like you can find. I've often thought of like, do like a cat's cradle thing where you have like a generative net in your hand and you're like trying to capture birds or something. Something where it cares about the body. But yeah, like there's lots of games. There's not going to be anything where like, we have like full motion games that do lots of cool 3D tricks, but like people stop playing VR Skyrim to play like Galaxy Express or whatever the Cosmic Express.
Yeah.
It's not like, oh well, I guess we don't need Bitly anymore. Yeah.
Is there a stark difference when you show a lot of what you showed was just fantastic for people who are very adept with their bodies. Is there a stark difference when you give this to them versus give this to people who aren't acrobats or dancers or whatnot?
The kids loved this thing. So I think it's actually, it helps because a lot of this stuff has a smoothing effect. So it was actually fun with some of my early Leap Motion, my early Kinect experiments on the V1 of the Kinect, where like, I don't know if you remember the V1 of the Kinect, but like it would drop frames just constantly. And so even if I had like my skeleton doing this, I had like Kinect Toy, which I write about in the paper, and because they're particles with a force, they have perfectly smooth forces even as they're following something that's doing this. So it's got a kind of a natural assistive smoothing effect that makes small bad gestures into big beautiful ones. Yeah.
What do you think is the potential for something like this for facilitating social experiences?
Really strong. Catherine Isbister has done a lot of this. She's actually got one where it's the sort of performance aspect. You're two people and you're kind of playing a dance game, but it's about matching the other player's movement. And she found that in that there's a lot of out of the screen communication going on. Of like, if I'm dancing with a bad dancer, I might make smaller, clearer gestures to try and get them on board. But it's also about kind of coming up creatively with different things.
Yeah.
So yeah, there's a lot of like, my dissertation is about creativity for casual users, and like one of the big exclamation points that I found with that is how much creativity is socially linked.
Yeah. Well, one of my, this is a quick follow-on, one of my students in my generative methods class is, they got really interested in this kind of improvisational dance where it's like everybody in a group and people just kind of spontaneously take on leadership roles. I don't remember what it's called. I think it's called passing through style thing. It's like a Venezuelan like social kind of folk dance, and it's like someone will just start doing something, and then maybe the other people around them will start imitating that. They'll start walking in a circle, and people will follow them. But then people can break off from that and choose various kinds.
Yeah, it's really interesting to see the way that like rules happen in dance, and this is why I'm big into like looking at traditional forms of dance. Because like square dancing, mat dancing, they have sort of augmented rules already. Like the color is an AI that is yelling at what you're going to do next. And so there's a position I think for a color style AI. You can also think of like the twister spinner as an AI that's giving you permission to make certain dance moves. It's like permission, getting called on. Like what if you're the shy one in the group and the AI puts the big pointing red arrow in front of you, and you have to, like if you're at a wedding dancing in a circle and you get pushed out in the middle and you have to do the dance until you can get back to the slide.
I really enjoyed watching this, and I can imagine it's fun doing it. But what I'm wondering is it always easy to have nice visual effects or does it sometimes also require practice and difficulty?
I suspect it's one of those art forms where it is now effortless to me because I know how to move through it without encountering any of the obstacles. Generometers were very helpful for this, of like, if you find yourself trying to get from input A to output B, and there's no connector, and you have to go through some horrible, like I was doing with the, trying to get the Z dimension, and it was bad and not good and hard. Oh, go ahead.
I'm not sure if I made myself clear, but do you purposefully include challenge
I do.
for the for your
I'm
game?
not particularly interested in challenge, just because it's not part of my aesthetic experience.
Okay.
You could figure out what that means for your own work. Yeah. It would be one of those ones where you would have to figure out a way to do challenge, or like ideally you would figure out a way to do challenge that also kind of participates in the dance space. Not just like a stop the music, stop the interaction, shutdown thing, but in a way that's like, kind of in the way that like Sims and Max's games fail in a way that's fun in the simulation. Have something that like shows you that you're failing while not stopping the dance. Don't drop it. Or do if that's part of your aesthetic. All right.
All right, that's it for us for this morning section. We've got an hour for lunch. I have no idea what that looks like. But then we'll be back here in an hour, 1 p.m., whatever time zone this is in, with the next section.
I sent you